Let's talk about finding the molecular ion in a mass spectrum. So the molecular ion is going to be the total mass of the whole molecule, giving us the molecular weight of the compound being analyzed in its ionized form. It'll also, by definition, be the highest mass in the spectrum that is not due to heavy isotopes of the same elements of a molecular formula. We'll look at what that means in just a moment. We're only going to consider the lowest isotopic mass of the entire molecule. It will not result in unreasonable fragments as well. And so if we see that we're losing something off of the molecular ion that's less than, say, a CH3, which is equal to 15, so we'd call that molecular ion minus 15 would be the loss of a methyl radical, for example, from a molecular ion. Anything less than that's probably going to be an unreasonable fragment, okay? And so that is a major fragment. 1 or 2 hydrogens, that's fine, but a major fragment that would be higher than, a few percent is very unlikely from the molecular ion. Okay, and there are others as well, but that's just for example. We'll see an example or two and more in class. And with carbon, the isotope effects that we're talking about, the molecular ion is going to contain carbon-12 and carbon-13. And so suppose we have a molecular ion that has 10 carbons. The odds of finding a carbon-13, which is 1.1% of all carbon, gets multiplied by 10 in this case. So the odds of seeing one carbon-13 out of 10 carbons is going to be 11%. And so what we'll see is we'll see out of 100%, we might see an M+1 peak. Here's our molecular ion here. We might see an M+1 peak that is 11% the height of our overall molecular ion. And so it won't be the base peak. The molecular ion may not be the base peak, but if we reference our height of the peak here to our molecular ion, it's going to be 11%, or very close to that statistically, to the molecular ion. And so if we see that this M+1 that we think we have is actually more, if we think we have C10, if it's somewhere, if this was 10% and we have 100% here, if it's more than 50% or more than 11%, maybe 15% or more, then this is actually the molecular ion and not the previous peak. And so it's not due to isotope if it's greater than 11% with 10 carbons. Okay, and so if there were 11 carbons, it'd be 11 times 1.1%, and so on. So that's what we're allowed to have. And if that number, if that percentage is greater than what we're allowed to have, then that means the molecular ion is the next higher peak and not the previous peak. So to recap here, this is due to isotope effects. This peak is not due to isotope effects because it's too large to be an isotopic peak with carbon. Okay. With bromine, it's a lot easier to see because when we have bromine 79 is about 50% of all carbon. It's not exactly 50%, but it's close. And what we're going to see is a ratio of bromine 79 to bromine 81 of about 1 to 1. So in our spectrum, you're going to see a molecular ion, say it's at 179. Okay, well, you might have at 181 an M+2 peak that is an isotope peak of the molecular ion, and then you might have a carbon-13 peak of each one of these that is an M+1 or an M+3, but the molecular ion is going to be the lower of the two. So in a spectrum with bromine, you're going to see a series of doublets until you get to a peak that results from the molecular ion minus 79, which is equal to bromine. So loss of bromine from your molecular ion is going to be a major peak. That's where the doublets will stop. But you'll see great evidence of bromine all through your spectrum by these doublets that you'll see, because they're about 50-50 bromine 79 to bromine 81. And when you're calculating your molecular formula, be sure you're using bromine 79, because on the periodic table, the mass of bromine is about 80 because it's an average of those two. So you want to make sure you're using the lowest isotopic isotope for your calculation of mass for the molecular formula. With chlorine, it's about 3-to-1 instead. So what you'll see is a 3-to-1 peak series. So the molecular ion here will be this peak, an M+2 that's about a third the height of the molecular ion. And you'll see a series of these. You know, if we have a molecular ion here, we've got our spectrum. You'll see a series of these types of peaks leading to an M-35, M- chlorine peak where the doublets stop in your spectrum. But you'll see these 3-to-1 doublets going down at M+2 when chlorine is present in your mass spec. Okay, and we'll see more examples of that in class as we go and in the book. With nitrogen, on the other hand, the way we tell nitrogen is by the molecular ion being odd. If there's an odd number of nitrogens, that means the molecular ion will be an odd mass. In all other cases, you have an even molecular ion. And so in the normal case, what we'll see is we'll see even molecular ion and odd fragments. With a nitrogen present, you're going to see the opposite. You're going to see odd molecular ion with even fragments. And so when we analyze a spectrum, we'll see how that works. And that's an easy dead giveaway for nitrogen. It only works this way for nitrogen. With alcohols, often we won't see the molecular ion because of the decomposition of the molecular ion is very favorable. It's very fast. And what we will see is we'll see odd fragments and then an even M-18 peak that may not even be the highest mass. And so if we look at this alcohol that we have here, as I've labeled the spectrum, we see that we've got odd fragments, and then we have this mysterious even fragment here. We know that unless nitrogen's present, our fragment should be odd, our molecular ion should be even, but we don't see a molecular ion. We need to see an even number somewhere out here that could be our molecular ion when nitrogen is not present. And so we know something's wrong. So what we look for are these even clues here. This is likely due to an alcohol, and this is an M-18. This is loss of water. So this is minus H2O, loss of water from our molecular ion. And so we can figure out what the molecular ion should be by saying 84 plus 18, and we're going to get that that's 102 is our molecular ion, but it's too unstable. It doesn't make it all the way down to the detector. So when we say 102, we check to see if the fragments are realistic, and we see that from 102, this 87 would be an M-18. That's loss of methyl, so feel pretty good about the molecular ion being 102 here due to that loss of water. And again, the way we could tell is because of the odd fragments and the even peak that's not high enough to be the molecular ion. To be a molecular ion, you've got to be the highest mass, not due to isotopes, and give reasonable fragments.